Hello everyone. Today we are going to study law of conservation of mechanical energy. In last lecture we studied that non-conservative force and potential energy. A force is called non-conservative if work done by the force on a particle that moves between 2 points depends on the path followed by a particle between these points. And the best example of non-conservative force is a frictional force. The total work done by the force of friction in round-trip journey is W is equal to minus 2 mu mgs, where mu is coefficient of friction between the block and table, m is mass of the block, g is acceleration due to gravity, and s is displacement. And the energy possessed by a body by the virtue of its position or configuration is called potential energy. There are different forms of potential energy such as gravitational potential energy, elastic potential energy, chemical potential energy, and electrostatic potential energy. So let us study law of conservation of energy. The conservation of energy is one of the most important concepts in physics. It does not only apply to mechanics but is a universal truth. It states that energy can neither be created nor be destroyed, but can only be converted from one form to another. For example, electrical energy to kinetic energy and to potential energy. Conservation of energy is one of the fundamental law and it is always obeyed in all processes taking place in the universe. We know that energy can exist in various forms. Whenever energy in one form disappears, an equivalent amount of energy appears in some other form, so that total energy remains constant. Thus, the principle of conservation of energy may also be states that total energy of a system remains constant as long as the only forces acting are conservative forces. The sum of kinetic energy and potential energy of the system is called mechanical energy and is represented by capital E. Hence, E is equal to K plus U, which is equal to constant. The relationship implies that the total mechanical energy of a system is always constant. If the potential energy is at a maximum, then the system will have minimum kinetic energy. And if the kinetic energy is at a maximum, then the system will have minimum potential energy. We know that for conservative force, the work done is independent of the path and depends on endpoints or positions. To understand the change in potential energy of a particle, consider a point P at an arbitrary location as shown in figure. So this is position of a particle at a point P. This is position A and this is B. So particle will be suppose move from A to B along path 1. As the force is conservative, so it goes to its initial position along path 2. So this figure shows change in potential energy of a particle. So The work done by a conservative force F on a particle in moving from position A to B is work done from A to B is equal to integration vector F dot dr from A to P plus integration vector F dot dr from P to B. The work done in moving the particle from P to B depends on the position of B. Thus, if we go to some other point, we get different work. Suppose this function of position as minus u. So, the work done in moving a particle from P to A is integration vector f dot vector dr P to A is equal to minus u of A, or if we reverse the limits, that is integration vector f dot dr A to P is equal to plus u of A. This is equation number 1. Similarly, the work done in moving a particle from P to B is integration vector f dot dr P to B is equal to minus u of B. This is equation number 2. As we get these two equations, therefore we get total work done in moving a particle from A to B is, that means we have to substitute values, integration vector f dot dr from A to B is equal to integration vector f dot dr A to P plus integration vector f dot dr P to B. Using equations 1 and 2, we get W is equal to U of A minus U of B. Initially, the particle is at the position A and finally particle is at B. Means we can write U of A as a UI and U of B as a UF. The work done by conservative force in moving from initial to final position is W is equal to UI minus UF, or minus W is equal to UF minus UI. The quantity UF minus UI, which is equal to delta U, is called change in potential energy. In a system of particles, let UI be the initial potential energy and UF is final potential energy. According to definition of change in potential energy, that is UF minus UI is equal to minus W. This is equation number 3. W is the work done by the conservative force on the system as it passes from initial to final position. If there are no other forces such as external force acting on the system, the work done by them is 0. According to work energy theorem, we can write W is equal to Kf minus Ki. That is change in kinetic energies. This is equation number 4. From equation 3 and 4, we get UF minus UI is equal to minus Kf minus Ki, or UF minus UI is equal to minus Kf plus Ki. Means UF plus Kf is equal to UI plus Ki. Means equating initial and final terms. The sum of kinetic energy and potential energy of the system is called mechanical energy. and it is denoted by E. Means we can write E is equal to K plus U is equal to constant. If only internal conservative forces work. When only the internal conservative forces work, then the total mechanical energy of the system remains constant or conserved. This is called principle of conservation of mechanical energy. If non-conservative forces such as frictional force, air resistance force act between the system, then the total work done on the system is W is equal to WC, means work done due to conservative force, plus W other, work done due to other forces. According to work energy theorem, our equation becomes WC plus W other is equal to Kf minus Ki. For conservative forces, minus WC is equal to UF minus UI. We know this equation. So we can write UI minus UF plus W other is equal to Kf minus Ki. Or W other is equal to Kf plus UF minus Ki plus UI. Or Kf plus UF means K plus U is total energy. So EF means total final energy minus EI. So we get W other is equal to EF minus EI. This equation shows that work done by all forces other than internal conservative force is always equal to change in mechanical energy of the system. Then example of conservation of energy. We know during the motion of a ball through air, total mechanical energy is same at every point in the motion, provided no force other than gravitational force work on the ball. In this example, a ball and earth forms a two-body system as shown in figure. During the motion of a ball, only gravitational force work on a ball. And when the ball moves up, that is from position A to B, this is example of conservation of energy. This is Earth's surface. Ball moves from position A to B, B to C. Then what happened? As ball moves from A to B, then kinetic energy decreases and potential energy increases. And from B to C, its kinetic energy increases and potential energy decreases. In general, principle of conservation of energy states that energy can neither be created nor be destroyed. It is only transferred from one form to another form. Means in this case, total energy remains constant. As kinetic energy decreases, at that time potential energy will be increases, so that total energy remains constant. Similarly, when ball goes from position B to C, kinetic energy increases and potential energy decreases, so that total energy remains constant. Kinetic energy decreases but potential energy increases such that total mechanical energy of the ball at every point in the motion remains constant. When the ball moves down, that is from position B to C, its kinetic energy increases but potential energy decreases such that total energy remains constant. Figure shows gravitational potential energy. This is position of a body. H is the height between the position A and B. Any material body and Earth form a two-body system. But to calculate the gravitational potential energy of the body, place at a vertical height h above the surface of Earth. M is the mass of a body at a point A on the surface of the Earth. The force acting on the body at a point A is mg, which is downward direction. To move the body from A to B, a force which is equal to mg applied on the body in upward direction. The work done by the applied force on the body is force into distance covered. Force is mg and distance covered is h. So, work done is mgh, where g is acceleration due to gravity. This work done is stored as a gravitational potential energy at a point B. Hence, potential energy at a point B is equal to mgh. This is change in potential energy of the body in moving from A to B. But potential energy of the body at the surface of the Earth equals to 0. The potential energy of the body at a point B is equal to mgh. Means at a point A it is equal to 0 and at a point B is equal to mgh.